Imagine trying to assemble like a massive, complicated piece of IKEA furniture, right? But the manual consists entirely of raw text.
Oh man, that sounds like a complete nightmare.
Right. Like insert peg A into slot B at a 45-degree angle relative to panel C. There's no pictures, no diagrams of the little cartoon person holding a wrench, just paragraphs of spatial instructions.
You'd probably lose your mind before you even got the frame together.
Exactly. You would. Yet in 2026, some of the most advanced programming ecosystems in the world are, well, they're forcing software developers to do exactly that when they try to document complex systems.
Yeah, we are looking at this bizarre structural blind spot. We expect modern software architecture to be, perfectly mapped and visible, but the moment you try to render visual assets like architecture diagrams or scatter plots into a manual, that blueprint often just falls apart.
Welcome to the deep dive. If you're listening to this, you're probably someone who wants to bypass the endless, overwhelming flood of information out there and get straight to the aha moments.
Absolutely. You want to understand the underlying mechanics of why things are happening in tech, not just what is happening.
Right. So today, we're custom tailoring an exploration into a 2026 presentation by developer at Look036. It's titled Visual Documentation, Python versus Rust Asset Pipelines. And our mission here is to explore a hidden, but honestly, absolutely crucial bottleneck in software engineering.
Right. We're looking at how the tools we use to document code handle or, well, completely fail to handle visual assets.
And we really need to frame this as a story of ecosystem maturity, I think. Why does Python, a language with over 20 years of history, process images natively, while Rust, which is this incredibly modern, beloved language, pushes developers into a corner where they sometimes just abandon images entirely?
It's a huge contrast, and the implications of that contrast, they really ripple out across the entire software industry.
Yeah, so let's start with the absolute necessity of visual documentation.
Mm.
Because for mathematical and geometric libraries, a lack of figures doesn't just make things like a little inconvenient.
No, it fundamentally breaks the learning experience.
Right. If a developer is trying to understand a physical design algorithm, describing that geometric output purely in text is an exercise in futility. The user ends up burning massive amounts of cognitive load just trying to mentally visualize a spatial distribution.
Instead of actually understanding the logic of the code itself.
Exactly. A simple scatter plot tells the whole story in a millisecond. So why is simply putting a picture in a document such a massive hurdle for modern systems?
Well, if we connect this to the bigger picture, it really comes down to the asset pipeline gap.
The asset pipeline gap.
Yeah. See, when a developer writes code and adds an image to their documentation, everything looks flawless on their local machine. The image file just sits securely in a folder right next to the code on their hard drive.
Right. The local tool finds it and shows it.
Exactly. The local documentation tool scans the directory, finds the file, renders it on the screen, and the developer thinks, great, job done.
But the moment they push that code to a hosted platform like Read the Docs for Python or DocStars for Rust, the images just vanish. You get that infamous broken image icon.
Yeah, and that happens because documentation generators like Sphinx for Python or RustDoc for Rust, they operate essentially as web compilers. They're building a static site from source files.
Right.
So if the documentation tool doesn't possess explicit instructions that say, hey, this specific image file is a crucial documentation asset, the compiler simply leaves the image behind on the local machine.
So a published version on a web server is left looking for a path to an image that was never actually uploaded.
Exactly. It's completely severed.
Okay, let's unpack this.
Yeah.
Because this is where the Python ecosystem demonstrates the power of 2 decades of polish. Python handles this exact pipeline problem using a tool called Sphinx, right?
Yeah, Sphinx. It operates as this mature, all-inclusive ecosystem that solves this natively out of the box.
With 0 extra runtime dependencies required for static images, which is huge.
Right. Sphinx has had the luxury of time to refine this workflow. It parses restructured text, or RST, and uses specific directives.
Like the figure directive, right?
Yeah, exactly. When the Sphinx compiler hits a .figure directive for a static image, it immediately recognizes it as a dependent asset. The pipeline automatically creates an underscore images directory in the final build output, copies the local file over, and this is the best part, it dynamically rewrites the HTML paths.
Oh, wow. So whether you used a relative path or an absolute path in your source code, Sphinx normalizes it so the web link never breaks.
Precisely. And it also provides native directives like .svgbob for converting ASCII art into diagrams and .math for equations.
But I think the truly fascinating part of the Sphinx ecosystem is how it handles dynamically generated visuals using the plot directive.
Oh, yeah. That's where the magic really happens.
Because when you build the documentation, the pipeline doesn't just look for an existing image. It spins up a Python interpreter, executes the Python code written directly in the docstring, captures the resulting plot data, saves it as a PNG file, and embeds it right into the HTML.
The profound implication here is that the source code literally is the figure. Sphinx maintains the state and memory of that execution during the build.
Meaning the image is never stale.
Exactly. If someone updates the underlying algorithm in the library, the documentation's graph automatically shifts to reflect the new output. You've completely removed the human element of, manually generating a new graph, saving it, and updating the repo.
Wait, I do have to push back on this approach, though. If the documentation tool is literally running the code and generating plots every single time it builds the manual, doesn't that inherently require heavy runtime dependencies?
It does, yeah.
Like, you would need the entire matplotlib library, potentially NumPy or SciPy, installed on the documentation server just to build a text-based website. From a systems perspective, isn't injecting heavy external visualization libraries into a documentation build step incredibly fragile?
Well, your concern hits on a classic trade-off in software engineering, right?
Yeah.
Build time wait versus long-term maintainability.
Right.
The server absolutely must have matplotlib and those scientific libraries installed. However, looking at the data presented by @Look036, the sheer success of this approach kind of outweighs the dependency costs.
Really? How so?
Well, they tested 4 distinct Python projects: LDSGen, Netlist Docs, FizzDs, Pi, and Alelgo. Across those projects, the build process generated 13 complex dynamic plots and ASCII diagrams, and the execution yielded 0 warnings.
No. 0 warning.
Yeah, and the setup cost for the developers was microscopic. They merely had to add a single line of code to enable the extension in their conf.py configuration file. The friction is almost non-existent.
So Python developers essentially have an automated infrastructure where their charts draw themselves.
Yeah.
That's amazing. Which brings us to the stark contrast of Rust.
Right.
Rust is celebrated for its execution speed, memory safety, incredibly modern tooling. Yet when it comes to visual documentation, Rust is currently trapped in this structural bottleneck.
Yeah, the built-in documentation tool for Rust, CargoDoc, operates under a very strict set of rules regarding directory isolation. For security and predictability, Cargo focuses almost entirely on the sekrc directory where the source code lives.
Okay.
So when Cargo builds documentation for the main Rust hub, docs.dars, it parses the code to build an abstract syntax tree. If a developer places a PNG image in a separate docs or assets folder, Cargo's compiler basically considers it outside its jurisdiction.
It fundamentally does not package or copy files outside of that source scope. So the images are just dropped entirely during the web deployment.
Exactly. And we are seeing real-world casualties because of this architecture.
Yeah, the source mentions a striking quote from 2024, right? From the developers of the Rust GUI framework, Masonry.
Right. They stated very clearly, we considered a lot of alternatives. All of them were pretty fragile. We ultimately decided not to include all images.
A framework designed specifically for building visual interfaces had to abandon visual documentation because the pipeline friction was just too high. That is wild.
It is. And it creates a ripple effect across massive domains in Rust. Libraries like eGui and Slint, math ecosystems like Nelgebra, plotting tools like Plotters, and computer vision libraries like RustCV.
They're all struggling to show users what their code actually produces.
Exactly. Without native asset bundling, developers are forced to engineer their own workarounds, which introduces deep technical debt.
Okay, here's where it gets really interesting. The Rust community engineered a workaround using a crate called embed doc image.
Right.
Wait, so to get around Cargo ignoring the image files, developers are using base64 encoding to jam a PNG directly into an HTML data URI at compile time. Doesn't that cause massive web bloat?
Oh, it absolutely confirms the bloat. The physics of base64 encoding dictate that. See, base64 translates binary data into a 64-character ASCII alphabet. Because it takes 4 ASCII characters to represent 3 bytes of binary data, you automatically incur a 33% increase in file size simply by encoding it.
Wait, 33% just for encoding?
Yeah. A standard 100 kilobyte PNG file swells to over 133 kilobytes of raw text embedded in the HTML.
That's insane. So if a page has 10 architecture diagrams, you are forcing the user's browser to download and parse megabytes of text data before rendering a single pixel.
Precisely. So developers have to add aggressive optimization steps just to counter this. They have to run tools like Oxaping or Pinquant to compress the original images as much as physically possible before the conversion.
Just to keep the documentation page sizes from timing out on slower connections.
Right. And furthermore, if an image file is accidentally moved locally, the embed doc image crate triggers a hard compile error. Your entire software build crashes because the compiler cannot find the image file to convert into text.
So you end up with a brittle pipeline. The exact fragility the Masonry developers were trying to avoid becomes a mandatory part of your CI process.
Exactly.
But, leveling the playing field here, the narrative does shift. Rust isn't failing across the board. There's a specific visual domains where Rust matches Python perfectly right out of the box.
Yeah, inline equations are a perfect example of that. Both Python and Rust use standard syntaxes for math. In Rust, a developer simply wraps their mathematical formula in double dollar signs.
And when CargoDoc generates the HTML, it relies on client-side rendering engines like KTeX. Because the math is just text, there are no binary assets to lose.
Exactly. It renders beautifully on docs.tars.
Yeah.
And the other major win for Rust is the Ask It to SVG pipeline. The SVG Bob doc crate, which has over 1.6 million downloads, handles diagrams brilliantly.
Right, a developer can draw a flowchart using standard keyboard characters, dashes, slashes directly inside their code comments, and the tool converts that text art into a crisp inline SVG natively.
What's fascinating here is the philosophical difference in approach. While Python executes a script at build time to draw a picture, Rust leverages its powerful macro system to handle visual rendering at compile time.
Wait, I want to dig into those mechanics. How does the compiler actually intercept a text comment and turn it into a graphic before the program even finishes compiling?
It uses a specific procedural macro, usually invoked as transform. During compilation, when the Rust compiler is reading the code, it reaches this macro. The compiler literally halts standard evaluation and hands the raw ASCII text of the diagram over to the macro.
Oh, wow. So the macro acts as an independent mini program.
Exactly. It parses the text, computes the geometry, generates the corresponding XML code for an SVG image, and then hands that XML back to the compiler.
And the compiler just seamlessly embeds that XML directly into the documentation string.
Yeah. The language itself is doing the heavy visual lifting from the inside out.
It's deeply elegant, but I imagine it introduces a different kind of architectural complexity, right? It's specifically around feature gating.
Mm-hmm.
Running complex XML generation macros at compile time has to heavily impact compiler speed.
It really does. If you're a developer running Hargo check 50 times an hour, you cannot afford to have the compiler waste CPU cycles redrawing SVG diagrams every single time you hit save.
So how do they manage that?
Well, Rust developers rely on configuration attributes known as CFG at PI. They set up feature gates that instruct the compiler only execute this heavy macro when we are explicitly doing the final build for the docs.
Okay.
And often this requires using nightly builds of the Rust compiler to access unstable features. It saves compile time, but it adds significant mental overhead to the project setup. You are basically trading Python's runtime dependency bloat for Rust's compile time configuration complexity.
So what does this all mean when we put these two pipelines side by side? Both ecosystems obviously face distinct pitfalls.
For sure.
Python possesses a highly mature pipeline, but relies on RST syntax, which can feel really verbose. Plus, you have those path resolution headaches.
Right, navigating relative versus absolute file paths. And conversely, Rust suffers from the base64 bloat, the friction of feature gating macros, and a complete absence of dynamic, auto-generated plots.
Right. In Rust, every single plot must be pre-rendered externally by a human, saved as a PNG, and committed as static technical debt. There's no evaluated build time magic.
But there is a horizon. The presentation outlines Rust RFC number 3397, which is a formal proposal to introduce native asset bundling directly inside RustDoc.
Which would fundamentally solve the core issue.
Exactly. Would allow Cargo to map and bundle external images with the same fluidity that Sphinx currently achieves. But that RFC is currently blocked pending a wider evolution of the Cargo source format.
So if you're a developer today building a scientifically complex application, the reality is that Python has had this infrastructure perfected for over 20 years, making it the undisputed king for data and science documentation right now.
Yeah. This raises an important question about the life cycle of languages, We spend massive amounts of energy debating syntax, execution speed, memory safety.
Sure.
But the struggle with asset pipelines proves that a language's success isn't just about the code execution itself, it's about the invisible infrastructure. If the ecosystem doesn't allow a community to visually communicate complex concepts, the raw speed of the language becomes irrelevant.
Knowledge transfer is just as critical as compilation.
Exactly.
Well, thank you for joining us on this deep dive into Atlas 036's presentation. The ultimate takeaway here for you listening is to never underestimate the power of pictures in documentation and, appreciate the hidden pipelines that put them there.
Yeah, we often treat documentation as an afterthought, but the engineering required to render it seamlessly is a massive undertaking.
It really is. Before we sign off, though, I want to leave you with one final provocative thought to explore on your own. We spent this time analyzing how pipelines like Sphinx execute code to generate static plots. But what happens to the asset pipeline when AI and WebAssembly fully integrate into documentation platforms?
Oh, that's a wild thought. The concept of a static manual disappears completely.
Right. Could the future of documentation bypass PNG files entirely? Imagine a pipeline where the source code spins up a personalized, interactive visual simulation running natively in your browser.
An AI driven generator that reads the code and renders a live 3D model of the data structures just for you.
Exactly. No broken directory links, no bloat. Just a living blueprint that adapts to exactly what you're trying to build. The future of software manuals might not be something you read, but something you interact with. We will catch you on the next deep dive.
Until next time.